Hello, everyone. Welcome back to the channel Physics Cafeteria, where we do discuss physics. And right now, we are focusing on the Griffiths based QM series. So, we are going to continue the quantum mechanics series by taking the topic of normalization. Here, I am very interested to describe what is normalization and what are the physical aspects of that. And the second question which arrived in my mind is, why do we need it in quantum mechanics? So as we discussed earlier, that quantum mechanics looks mysterious, but at its heart, it's actually deeply statistical. So that one subtle question in my mind is, why do we impose the normalization condition on the Schrödinger equation? Is it a mathematical trick or physical necessity? So let's understand this in the most intuitive way possible. So in classical physics, when we have a wave, it is having a clear amplitude. A bigger amplitude means the wave carries more energy. But a quantum wave function psi of xt doesn't carry energy this way. It does something much more profound. Psi of xt square, that is probability density. And I guess we have discussed enough in the previous videos. If you have not watched it, I would suggest please go to the channel and revisit the videos. So psi of xt tells us the probability density of finding a particle at position x at time t. So instead of energy, the wave's height encodes the information, and probability must obey one universal rule, and that is total probability equals to 1. After all, the particle must be somewhere. So let's impose the condition, and this condition is integration from minus infinite to plus infinite psi square dx equals to 1. This is called normalization. It is not optional. It's not a mathematical decoration. It's physical constraint. So normalization converts an arbitrary mathematical solution into a physical one. Now the question is, why is this needed? To understand that, we must look at the Schrödinger equation itself. That is h psi equals to e psi. This equation is linear and homogeneous. That is the property. And it's a spatial property, I would say. So if psi of xt is a solution, then c into psi of xt is also a solution. I would say that is a scaled solution for any constant c. A classical wave has amplitude. The larger amplitude, the more energy. So that's what we have discussed. So the equation itself fixes only the shape of psi, not the overall scale. But if psi determines probability, then scaling it arbitrarily would give you the answers of probability which would be greater than 1, probability less than 0, or infinite, and that is totally unphysical, right? The Schrödinger equation doesn't know anything about probability. It only tells us how psi evolves, how the shape changes over time. But to interpret psi physically, we must impose the rule. And that is normalization. So the solution gives the shape, but normalization gives the physical meaning. So once we want to understand what is the normalization condition, and if psi evolves with time, will it be required that we should apply normalization condition with respect to time, or it is just the case only one time we impose on the Schrödinger equation, it will give the physically possible results. So normalization comes in when it converts arbitrary mathematical solution into physical one. So here we are going to check whether the normalization condition evolves with time or not. So d by dt of normalization condition, which would be integration from minus infinite to plus infinite psi of x square dx equals to integration from minus infinity to plus infinity del by del t of psi of x square into dx. So once we take the derivative of psi square del by del t, we can write this psi square mode of psi square in terms of psi star into psi. So let's do the differentiation, that is del by del t of psi star into psi. So we'll get psi star into del psi by del t plus psi into del psi star by del t. This is about the product rule. So del psi by del t gives us IH cross by 2m into del square psi by del x from minus I by h cross into v of psi. And the del psi star by del t equals to minus IH cross by 2m del square psi by del x square plus I by h cross v into psi star. So now let's expand this version by putting these two values into the above equation, this equation, and let's see how it evolves. So we can see this potential energy term is being cancelled out here, and we are getting these two terms. And let's just take some terminologies which are common in these both terms, and we do the del by del x, we separate it, and moving further we can get these results, that the d by dt of integration from minus infinite to plus infinite psi of x t square dx, that is equals to minus infinity to plus infinity del by del x IH cross by 2m psi star del psi by del x minus psi del psi star by del x into dx. So if we apply the limit, we can get this equals to 0. That means once we have applied normalization condition onto the Schrödinger equation, we do not need it to apply for any instant of time. So we'll get to 0. So normalization is a physical constraint. It's not a mathematical one. And that's why it is giving us the answer 0. So the probability is conserved. That's why once we normalize the wave function, we don't need to renormalize the wave function during time evolution. So yes, and this is incredibly important. Quantum mechanics obeys a probability conservation law, which is analogous to fluid flow. That means psi is normalized one, it remains normalized forever. Probability is conserved, so we don't need to renormalize during the time evolution. Think of psi of xt like a brightness of a spotlight across a stage. The brightness pattern can be any shape, narrow, wide, multiple peaks, but the total brightness must equals to 100, because the actor must be somewhere on the stage. And that is why we are getting brightness, and that is must equal to 100%. Normalization is like turning the dial so that the total brightness is exactly 100%. You can't have 300% brightness. That would be unphysical. You can't have 0% either. That would mean the actual actor vanished. So many students ask, why are we adding an extra condition to Schrödinger equation? Isn't that cheating? But it's not extra. It's the bridge between math and physics. Normalization is a physical constraint. Schrödinger equations gives you the infinite possible solution, but normalization picks out one that represents your particle. So yes, so the takeaway is that Schrödinger equation is linear and allows arbitrary scaling. Psi square is a probability density and must integrate to 1. Normalization selects the physically meaningful wave function. So once we normalized, the wave function stays normalized because probability is conserved. So Schrödinger gives the shape, normalization gives the physics. So if you found this explanation helpful, please like, share and subscribe, and continue following the Griffiths based quantum mechanics series. So in next episode, will look forward for the probability current and flow of probability in quantum mechanics. So thanks for watching. Hit like button, share and subscribe with your friends, and have a coffee.